Well, tunneling in karst environment, of course, is bringing a lot of challenges for the designers to ensure the serviceability of the tunnel over the years, but also brings and poses a lot of like quite severe risks for the first of all people, but also the machinery working in the underground. And therefore, the early detection or maybe even a prediction of any karst feature around or in the vicinity of a tunnel is a very vital information for all the people on the construction site. Well, geophysics is based on detecting some, as we call it, anomalies or some changes in different physical fields that are some signatures for changes also of the physical parameters in the underground. And fortunately, the one of the strongest changes and the most significant contrast is created between the air and the solid rock. So that makes the geophysics, as like the geophysical methods, as a very efficient tool for detecting and finding the karstic features in the vicinity of a tunnel. But however, this is the theory that sounds really well, but perhaps well the conditions in the tunnel are definitely not making it any easier. So the tunnel itself, the underground conditions are posing and bringing additional challenges for applying geophysics for detecting the karst features. I will try to shade this on the two examples that are coming from two major tunneling sites. They are quite similar, but both are major railway tunnels. So the one is 2DK and the other one is SBT. And the first example is a rather conventional concept that is applied also on 2DK, but also in the Semmering Base Tunnel in some certain section where the tunnel is crossing the carbonatic rocks, where we deploy a ground-penetrating radar on the tunnel invert, a temporary tunnel invert. That is a common concept for many drill and blast, many tunnels that are constructing using the drill and blast method, just because the tunnel invert is being open for at least a couple of days. It gives us the chance to do the measurement in an unreinforced tunnel invert. And the deployment of GPR is actually very straightforward. We just need to walk a few times there and back with a system that is as large as the system on the picture, and we can design it relatively accurately just based on the expected size of the karst features. Then we just deploy the number of profiles as we need, and usually we are able to detect karst features or karst phenomena to a depth roughly up to 10 meters. Sometimes, especially here on the 2DK, it can be also significantly more with the size of the target, well, at least 1 by 1 meter. This concept can be just used as a copy and paste for many tunnels, but the good thing is that it's extremely fast. The section that is 100 to 150 meters long requires roughly 1 hour in a tunnel. So the scheduling and implementation into the tunneling works is actually rather easy. And then also the delivering the results can be done within, perhaps up from 24 hours. Sometimes it takes longer, sometimes it takes less. Depends also on how urgent the requirement and the situation is. And when we do the GPR scan, we mostly get results that looks like that. This is a typical radargram, as we call it, radargram, where the strong changes of the black and white color is indicating the very strong reflection. That is for us an indication that there must be a significant change of the physical parameters in the underground. And the first example is showing a typical signature for airfield cavity that was also then later confirmed by drillings and filled with roughly 30 cubic meters of a grouting material. And this is kind of a typical and a normal way how the process is going. But on the second example, we see the similar but still a little bit different picture. That on the left side we see still a signal pattern that is very similar to the first scenario that indicates a presence of an airfield cavity. But just next to it is another area that shows actually almost no reflections that might imply, okay, that we have nothing relevant there. But actually, it's not true. The situation is like that. This is still a continuation of the cavity or the karst feature, but this section is filled with a sediment that is just because of a high clay content is fully attenuating the signal, and therefore we don't really see anything in that area. So we kind of just from the attenuation we can read out that there is a sediment-filled structure, but we have no idea what is located below, whether there is still some continuation of the airfield structure. And this area is for us, we can just do the interpretation with some certain limits. And on the third example, that is on the very right side, there is an example where the tunnel was partly reinforced with a metal reinforcement, or like the spray concrete reinforced with metal, which is completely disabling the electromagnetic waves to penetrate through the metal structure, and therefore this area is completely disabled for us for the investigation. So this is also the reason why the investigation with the GPR is mostly just done along the tunnel invert, or the open tunnel invert, just because the sprayed concrete reinforced with metal is completely disabling the application of the GPR. Currently, I guess there will be also a speech today on the topic that there is an emerging trend on using the fiber reinforced sprayed concrete that might also open the possibilities for application of the GPR also along the tunnel walls and all around the tunnel. That would significantly increase the applicability of the geophysical investigation in all directions, not just underneath the tunnel. That is, on the other hand, also the most sensitive area. Well, the second example is from Semmering Base Tunnel. That is a bit different. So this scenario is very specific, and compared to the previous example, much more complex. But actually, the task and the question was still the same. Could you please detect whether we have some cavities or some karstified zones around the tunnel? Well, the tunnel was excavated through the relatively short section of carbonatic rocks, and despite that there was very little to no karstification expected, roughly where also the cross passage was excavated and joining the main tunnel, the cavity with the volume of roughly 50 cubic meters occurred on the tunnel face. Was not completely air-filled, was filled with material and a lot of debris, water, and so on. But still, it was quite surprising to have such a feature in on the tunnel face. Well, the tunnel was excavated and also later hit this major anhydrite body that was also quite surprising for the geologists that it appeared over there. But however, it was then there came a task from the designer. Okay, so if he really had the karstification on the tunnel face, are we sure that there is no karstification around the tunnel? So can we be sure, or do we need to do some remediation of this zone? And this is how it came to us, because the first idea of the designer was just simply to confirm it by the drillings. However, that was stopped, or was not really supported by the geologists and geotechnical engineers, just because of this anhydrite body. If they would deploy a systematic raster of exploration drillings, they were kind of worried that they might come to anhydrite swelling, and that would just come with even higher deformations to the tunnel than they had. Therefore, they came to us that whether we can do something in this way, but without that the tunnel is already fully reinforced with a sprayed concrete or metal supported sprayed concrete, and no boreholes are to be done at this stage. So also no methods in boreholes could be involved. So our concept was based that densities and seismic velocities are the physical parameters we are looking at, and we combine the measurement of two different geophysical methods, seismic and microgravity. We did it. We did it in total 8 profiles all around the tunnel. So we covered really the area in the full radius around the tunnel, and it all took 5 field days, and the length of the section was roughly 150 meters long. So if I come back to the previous scenario where we had the GPR investigation on a stretch of 150 meters done within a couple of hours, that takes a couple of days. So this is a significantly higher effort that has to be invested. And based from the data we collected, so the data quality was really good, and we produced a lot of colorful images, because this is what we like the most as geophysicists, that we are producing colorful images that are showing different things. But we tried to compile it into a simplified model that could be delivered and easily communicated to the construction site. And we could define a zone that was located just some 20-30 meters after the cavity was encountered. It is shown by this red zone, and is actually just bordering the unhindered body, and actually sits on top of it. So that was actually one of the most critical points that we were trying to discuss with the local geologist, who was actually rather skeptical about that they hit really just the edge of the really massive unhindered body with the tunnel, and that it's ends just some 5-7 meters above the tunnel and also next to the tunnel. But really, thanks to a lot of input also from the geologists and from the designing team, we really agreed that the interpretation is the final one, and they admitted to prove it and to verify it with the boreholes. And actually, the boreholes were done just to verify the area, and on both locations, also on the outwarding wall, also above the tunnel, it confirmed that the unhindered body is really just ends just few meters out of the tunnel. And also on the top, it's like they hit really massively karstified zone, also with an open cavity in one of the boreholes that was more than 2 meters high. Well, just to conclude, the geophysics, can be a very efficient tool for targeting the boreholes, and you can significantly reduce the cost and the time needed for detecting the karst features around the tunnel. But on the other hand, well, even also in all cases, we need to be careful. What are we trying to detect? What are our limitations? How does the tunnel look like? How the tunnel is already built, in what stage? And this is all influencing the decision in which methods are to be applied. And then also, like, what size of the structure can be seen by the geophysical methods. And I believe that most of you are engineers. You like to ask questions like, is there a cavity or not? So, and you also expect an answer is yes and no. Unfortunately, in geophysics, that we are constantly facing the issue that we are just having or offering indirect diagnostic tools. So we can give you some interpretation that is based on some probability, but the more is the interpretation integrated with the other knowledge about the tunnel, the more we can be accurate and deliver information that is also useful for the tunneling. Thank you.
Thank you, David, and also sticking to the time strictly. Do we have any questions from the audience? Again, I'm going to say something. It's not going to be a question, but when we had the cave 54 in tunnel T1, there was an emergency call for David to come and do the geophysical testing using georadar to establish whether we have enough space beneath us with the solid rock to decide whether we should go over this karstic feature or do something else in terms of solution. So this comes as probably response to how important geophysics is in locating karstic features, which is the topic of your lecture. But this is the first-hand experience that happened last week. So this gives a weight to what you just explained. Is there any other questions or comment? If not, I would like to thank David for this lecture.